Hello everyone. In this video we want to show you how you can use the reactions that you have been studying in chapter 19, reactions at the benzene ring and reactions at the carbon side chain, to use those reactions in solving synthesis problems. I'll show you what I mean by an example. Starting with benzene, outline a feasible laboratory synthesis of para-chlorobenzoic acid. Now, I think it's pretty obvious there's no single reaction that will allow you to do that. And generally, these synthesis problems require a sequence of 2 or more reactions. Let's jump right to a possible solution to this. We'll propose this synthesis. We start with benzene. We do a Friedel-Crafts alkylation with ethyl chloride, aluminum chloride catalyst. You do have to use a large excess of the benzene. That'll make ethyl benzene. We then oxidize it, oxidize the side chain to the carboxyl group. That's the reaction that we've seen very recently. Then we chlorinate it, do a ring chlorination with chlorine and ferric chloride, and we're getting our parachloro product. If there's any ortho, we could remove that by chromatography. So this is just not saying this is the answer, but it's a proposed solution. So the question is, will this work? Take a look at it. Is every step going to work? Well, let me comment. The first reaction will certainly work. The second reaction, yeah, that's fine. The problem is this last reaction, because the carboxyl group is a meta-director, and we don't want meta-chlorobenzoic acid. We want para-chlorobenzoic acid. So that proposed synthesis is not going to work for us. So let's try an alternate approach. Now first, before we look at an alternate approach or alternate synthesis, a general comment on the strategy here. Organic chemists are challenged by this kind of problem all the time. There's a certain desired compound they want to make, and how are they going to do it? And often they have certain starting material. And how do you go from the starting material to the target compound? Well, the strategy that is very useful here is to actually start with the target compound that you're trying to make. Think of reactions that would make that target compound. Now, each reaction will involve some precursor to that target compound. So what you want to do is look at each of those reactions, look at the precursor, and think of a reaction that will, in fact, make that precursor. And the idea here is you're kind of thinking backwards. If you find a reaction that makes a precursor, think of a reaction that makes the precursor of that prior reaction, working away backwards, actually, to the starting material. And you're finding a route starting with the target molecule, kind of thinking backwards to ultimately the given starting compound. That's a general strategy that organic chemists use in synthesizing compound. It's called retrograde synthesis. So what is a better solution to our problem? Well, the precursor of parachlorobenzoic acid, our target compound that we used, which proved to not work, was benzoic acid. Benzoic acid to that compound. It won't work, as we mentioned, because a carboxyl group is a meta-director, not a para-director. This would make not parachloro, but it would make metachlorobenzoic acid. So let's try a different precursor, chlorobenzene. If we could make chlorobenzene, and I think you can see that you can make chlorobenzene from our starting compound, benzene, easily enough. Let's see if we can take chlorobenzene and find a synthetic route from it to our target compound. Well, all right, with chlorobenzene, you realize there's no way to hook on a carboxyl group as an electrophile. That's just not possible. But what we could do is attach a methyl group to the ring of chlorobenzene using a Friedel-Crafts reaction. Moreover, the chlorosubstituent on our chlorobenzene is an orthopara director, so that would put the methyl group in the right position. Any ortho product we get, we could separate that out by chromatography. Now, once we had the parachlorotoluene, if we can stick a methyl group in the para position of chlorobenzene. Once we have the parachlorotoluene, we can then oxidize it with a strong oxidizing agent, converting the methyl group to a carboxyl group. Boom, that will do it. And here is the synthesis from start to finish. We'll start with benzene, and we'll chlorinate it to make chlorobenzene, monochlorobenzene. Then we'll do a Friedel-Crafts reaction on it. The chloro is an orthopara director, so we'll get our parachlorotoluene. We'll also get ortho, but we can remove the ortho isomer by chromatography. So we now have this, and this is the right precursor that we want to get the product. Because if we now do an oxidation of that, this oxidation, of course, we learned about in the previous video, that will oxidize the methyl group to the carboxyl group, and there we are. This route shown here will indeed succeed in converting benzene to parachlorobenzoic acid. All right, here's another problem. Start with propylbenzene and find a synthesis route to 1-phenylpropane. So you want to start with propylbenzene and figure out a synthesis of this compound here. This would be, they have the name 1-phenyl-1-propene. Well, the idea of thinking backwards now, to make an alkene, we do that with an elimination reaction. We could start with this, or possibly the chlorine in the beta position here, and then do an E2 reaction. It's probably better to start with this because there is a way to make this compound from our given starting material. And we do that as follows. We take our starting propylbenzene, mix with it chlorine and light. That's a reaction we'd studied, learned about in the previous video. That does a selective attachment of the chlorine in the benzyl position here. The chlorine doesn't attach in any other positions because it's a radical reaction, and it's going to preferentially go through the more stable benzyl radical. And so the chlorine will attach selectively where we want it, attaching to that benzyl carbon. And then this benzylic chloride then would treat it with a strong base. It'll be E2 conditions, E2 elimination conditions will eliminate HCl, and we'll get our desired alkene product. All right. This really concludes chapter 19 of the assignments that are posted on Blackboard. We ask you to start working those. I also mentioned that I'm going to be sending an email. The time right now, it's getting actually close to class time on Tuesday night. It's 5:30, and I have to still render this video. That takes a little time. But I'm going to announce the posting of, oh goodness, I think this is quiz 5. That will cover chapter 18. and that will be posted. I think we're going to have that. Won't really have time to do it tonight, but I will post that tomorrow, Wednesday, and that'll be due on class time next week on Tuesday. All right. Thank you for watching.